Good afternoon, guys. Are you able to hear me?
Yes.
Okay. Yeah. We'll get started, guys. Just a minute. My software is a bit slow today. Yeah, guys. We'll get started. So we have completed 5 chapters, right? So what are the chapters that we have completed? We have seen till magnetism, right? So the topic that we are going to see today is electromagnetic induction. We are going to start with chapter number 6. Is my screen visible and am I audible, guys?
Yes, sir.
Yes. So we call it as electromagnetic induction, or we call it as EMO. Okay. Yes. So, what do you think this chapter is all about? If you see the fourth chapter, what was fourth chapter actually talking about? So, fourth chapter was saying that moving charges could produce magnetism, right? And the fifth chapter was speaking about the magnetism and its matter, right?
Yes.
That is about the permanent magnetism. So, if you observe this chapter, it is exactly the reverse of fourth chapter. So what do I mean by reverse of fourth chapter? So fourth chapter told that if you have moving charges, then magnetism can be generated. Then what does this chapter say? If there is magnetism existing, then from that you can generate back moving charges. That's what this chapter is all about. That is why induction is something getting generated. So what is getting generated? It is electricity that is getting generated with the help of magnetism. That is the reason why we call it as electromagnetic induction. Am I clear, guys? So there is the overall introduction of this chapter. Now, I'm going to show you a small simulation. See. So, I have a magnet in my hand. Okay. And there is a coil that is present. Right. And what happens to that coil? The coil is in turn connected to a bulb. Right. Now, this magnet has, somebody's mic is on, please switch it off. So this magnet will have a region of field lines around it. Are you guys able to understand? So it has a region of field lines, and if you look at the number of field lines that is passing through the coil, how many field lines are actually passing this?
One, sir.
So it is actually one. So it is actually one, right? Now, if I change it like this, then how many are passing? It is almost like three
Four,
field
sir.
lines. I'm four. Okay, I can say four. But yeah, I'm not talking about whether they are passing perpendicular or whatever it is. I'm saying number of field lines that are passing are four. Right. Now see, I'll switch off the field lines. Now this magnet is stationary and the coil is also stationary. Now the question is, when will this bulb glow? Right. So we know that any electrical device can glow or generate power only when there is a current flowing through it. Am I right? But if you observe, there is no current flowing through the coil. So this magnet is also in a fixed position. Now, if I take this magnet and if I move it like this, see what is going to happen. Did you observe what happened? Yes, guys?
Yes.
Right. So what is happening?
Current is getting produced.
So current is getting induced when the
Bring the
magnet is,
closer.
when you move the
Magnet is-
magnet. When you move the magnet, yes, it is happening. Okay, accept. Now I keep the magnet stationary. Now I will move the coil. Okay, I'm holding the magnet here. Now I'm moving the coil. Oh, sorry, I can't move in this. Okay, so in reality, what will happen is when you move this magnet or when you move the coil towards a stationary magnet, I repeat, when you move a magnet towards a stationary coil or when you move a coil towards a stationary magnet, then you can observe that there is some electricity induced in that particular coil. Are you able to understand? And this phenomenon is what we call it as electromagnetic induction. Because you're able to see it, and yes, you can do it. This is how an AC generator works. Right? But the question is, what is the theory involved behind? That is what we need to see. See, there is a phenomenon that is observed, right? But it is our job to ensure that we give a right theory to it, which supports the experiment that we saw with our eyes. Guys, are you able to understand? Right. Now, see, I will switch on the field lines. Now, you think, guys, if I have something like this, right? In this scenario, how many field lines are passing through the coil? Obviously, four, right? So when I move it like this, how many field lines are there?
Even more so.
See, but I will do one thing. Even before those lines, the curved surfaces start entering. See what I'm. Are you able to see? The number of field lines are not changing, but observe the bulb. Are you able to see some amount of glow?
Yes, sir.
So observe. If I connect a voltmeter, the voltmeter will show some deflection. Are you able to see the deflection? So when I move it closer, when I move the magnet closer, if the voltmeter showed deflection to the left-hand side, when I move the magnet away, it's showing the deflection in the right-hand side. But I'm trying to maintain some speed. So what I'm trying to say is, did I change the number of field lines through it?
No, sir.
No, sir.
I never changed. No, I am still holding the same number of field lines. But what is changing is an important question to answer. So till now, what were we thinking? If the number of field lines are changing through this, then we can say that the magnetic field is the electricity is getting induced. It is not the magnetic field lines that are changing. Rather, the concept is if there is a change of magnetic flux. So, if there is a change of magnetic flux taking place through a coil, due to the relative motion of the magnet or the coil or both, okay, if there is a relative motion existing between the coil and the magnet, then there is a current that is going to get induced. So, the first term that we need to see is what is magnetic flux. I'm sure you guys can define this very well. So, it is something similar to electric flux. So, what does magnetic flux mean?
The amount of magnetic field lines passing through a particular area.
So it is a number of magnetic field lines passing
Number
through
of magnetic field lines.
a given area, and how should it pass?
Magnetic field lines.
Normal to it. It should pass normal. This word is important, right? Because the definition of magnetic flux says,
Particular area.
yeah, you need to talk about the magnetic field lines that are perpendicular to a given area. That is what you need to be careful about. Okay, that is the first point. The second is, how do you think is going to be the formula for magnetic flux? Obviously, it is B vector dot A vector, where B vector stands for magnetic field and A vector stands for the area. Or there's also going to be B into A into cos theta. Right. So it is going to be BA cos theta. Right. So what is going to be the SI unit for it? So SI unit is going to be Tesla meter square. Because cos theta doesn't have any unit. This Tesla meter square put together is what is called as Weber, which is WB. Weber is the name of a scientist. So capital W and small b put together is what we call it as Weber. I'm sure we have seen that in the previous chapter itself under the name magnetic induction. Am I clear? So this is all about magnetic flux. Okay. So this is the basic introduction. Now the next question is, how is this magnetic field getting, how is the electricity getting generated? What did I say? How is it getting generated, guys? That change in magnetic flux through a coil generates an EMF. So what do we mean by EMF? It is the electromotive force, and this principle was first proposed by a scientist named Faraday. Okay, so Faraday was the scientist who proposed it. That is why this theory is also called as Faraday's law of electromagnetic. I'm sorry, guys, my software is not supporting today. One minute, wait. I will try to write in some of the software. Useless software. So please write it down. The heading is Faraday's law of electromagnetic induction. So what does it state? Change in magnetic flux through a coil induces EMF. I hope I'm clear with this, guys. Right. So here the reason why the word EMF is induced is because it is a potential difference under the open condition, right? So an EMF is going to get generated, and mathematically this is the formula that he has given. So Faraday is also a name of a scientist, right? So the EMF is directly proportional to the rate of change of magnetic flux. Okay, I can add this point with respect to time. So change in magnetic flux with respect to time through a coil induces EMF. So mathematically, E is directly proportional to d phi by dt. From this, we will write E is equal to minus d phi b by dt if it is of 1 turn. Whereas if the coil is of n turns, then what will happen is E will be equal to minus n into d phi b by dt. The coil is of n turns. Am I clear, guys? Is there any doubt in this? Are you guys there, first of all?
Yes, sir.
Yes,
Yes, sir.
Yeah. So EMF is equal to minus n into d phi b by dt.
That's a symbol for EMF, sir.
Yeah, this is for the EMF. Negative sign, huh?
Yes, sir. The negative sign comes.
So negative sign I'll explain because there is some other law. So negative sign is actually the significance of another law called as Lenz's law. Okay, this will be the next law that we'll be discussing. Anyway, before that, you ensure you write the statement. Did you guys finish writing this?
Yes, sir.
Okay. So this d phi b by dt is called as instantaneous change of flux. Right? This is called as instantaneous change. I'm sure by now you guys know what is the difference between instantaneous and what is the opposite of instantaneous change. It's called
Average, sir.
average change. So what can happen is EMF can also be written as minus of delta phi by delta t also. So it can be written as minus delta phi by delta phi by delta t if it is a coil of one turn, or you can write it as EMF is equal to minus n into delta phi by delta t if it is a coil of n turns. So let's do a problem based on this. See, I just want to explain. I want to show you something. What is there in your textbook? So the experiment which was performed by Faraday and Henry was something like this. So if there is a coil and this magnet was moved and this was fixed, okay, then you can observe that there will be a deflection in the galvanometer. When will the galvanometer show a deflection? Only when there is a flow of current, but we know that current can flow only when there is a EMF getting induced. Okay, in the second case, so here what they did is they used permanent magnet, right? So instead of using a permanent magnet, had they used a temporary magnet, means one is an electromagnet where the coil is connected to a electrical source, then this will generate magnetism depending on whether the switch is open or closed, and this will be the coil where the EMF will get induced. So the coil where the EMF is getting induced is generally called as pick up coil, because it is the one which is picking up the EMF. Okay. Next. In the third scenario, again, what can happen is you can control this whole thing, as I told you, with the help of a key. So if you observe, there is no key here, whereas there is a key here. Means in this case, what they're trying to say is, if this coil is generating a continuous value of magnetic field, and if this coil is moved, so what is happening in the first case and in the second case, there is a relative motion existing between the magnetic source and the pickup coil. Okay. Whereas in the third experiment, the thing that was observed is, this is the kind of setup. If you see, there is no arrow mark which shows the motion of either of the coils. So if coil 2 is connected to a battery with the help of a key, and coil 1 is a pickup coil, then depending on whether you keep the key closed or open, what will happen is the galvanometer will show a deflection here. Means here the relative motion doesn't change an important point. Relative motion is not an important thing, but what is important? It is the change of flux. So I want you guys to be very clear about this. So if somebody asks you, when will EMF get induced, what will you say? So let's say there is an MCQ question, okay, out of which I'm giving you two options. The first option is when there is a relative motion existing. So only when there is a relative motion existing between the magnetic source and the coil. I repeat it. The first option is only when there is a relative motion existing between the magnetic source and the coil. Second option is when there is a change of flux taking place with respect to time in the pickup coil, which is more apt option.
Change of flux, sir.
Yes. Okay. Because what does the third experiment tell us? See, this is how they frame MCQs. You need to be very careful. Same is the case with assertion and reason also. I hope everybody knows about the new pattern that they have brought. Okay. So for that, I'm just trying to frame certain questions, how they can ask. Right. In which the third part says that there is no necessity of relative motion, but if you're able to create a change in flux with respect to time, what flux? Change in magnetic flux with respect to time. Yes, you can generate EMF. That is the question. Am I clear, guys? So in the textbook, what they did is after the experiment observations, they gave the definition of magnetic flux and all those things. This you already know. Then I explained you about Faraday's law of electromagnetic induction. So E is equal to minus d phi by dt. Here the negative sign indicates I told it is something called as Lenz's law that I will explain. Don't worry. So E is equal to minus n into d phi b divided by dt. Am I clear, guys? Now,
Yes.
let's try to attempt a theoretical question where I want you to think an answer. Okay, don't look at the solution. The example 6.1 says something like this. Consider experiment 6.2. What was 6.2? 6.2 was the one with the pickup coil and with an electromagnet having moved towards the pickup coil, right? Consider experiment 6.2. What would you do to obtain a large deflection of the galvanometer? See, I showed you a simulation, right? I'll show you a simulation. I'll repeat the simulation. You guys look at it and tell me. See, in this case, are you able to observe? See, wait. Are you able to observe some deflection in the voltmeter? Right?
Yes, sir.
It is a very, very, very small value. Okay. Actually, they have put it as voltmeter, but they have drawn a galvanometer because for voltmeter, the reading will be to the left. Okay, there is a mistake in the diagram. But the voltage that is being shown is actually a galvanometer. Now, look at the bulb. No, read the question carefully. What are they trying to say? Yeah. What would you do to obtain a large deflection on the galvanometer? Can I say large deflection in the galvanometer will take place when the current flowing through it is more? That's what the principle of galvanometer told us. Flux is directly proportional to current sensitivity and all those things. Right? If that is the case, can I say that the bulb will glow with more intensity? Right. Now see. You're able to see? You're able to see the deflection. So what am I supposed to do? Since in experiment 2, the electromagnet is moved, what are we supposed to ensure that there is more deflection in the galvanometer?
Just brought the closest as possible to the.
That is
coil.
possible. So not about closest, you have to increase the speed also. That is there. But most important thing compared to it is, see, if suppose I repeat the same experiment, I have a magnet here, right? What had I repeated the same experiment with a magnet which is more stronger than this? So when I have a magnet which is more stronger than this, what would have happened? When I move it like this also, so now you saw the deflection. Observe the galvanometer. Now you saw some deflection in galvanometer, right? Had it been a stronger magnet than this, then the deflection would also be more. So the answer to that is you need to use a stronger magnet. So yeah, one of the things is you need to use a stronger magnet. But here, in this scenario, am I using a permanent magnet or a temporary magnet? Permanent magnet. But the question that they have asked is related to a temporary magnet. That is where we need to be careful again. Correct? So let's see. So this is the experiment they are trying to talk about. Right? They have used a temporary magnet. So what you can do with respect to this is, if you are able to increase, if you are able to change more amount of flux, I repeat it, if you are able to change more number of field lines through this pickup coil in the same amount of time, yes, you can make the galvanometer show more deflection. I hope that makes sense. So for that to be achieved, what are all the parameters on which flux depends? So flux is equal to BA cos theta. Okay, this is how you need to think, guys. I repeat it. Throughout the chapter, you need to think only based on this formula. Because change in magnetic flux with respect to time will generate EMF. Correct? So B is the magnetic field, A is the area of the coil, and cos theta is the orientation. Right? So to obtain large deflection, one or more of the following steps can be taken. One is use a rod made of soft iron inside the coil C2. So this coil is having vacuum in it. So it has a vacuum in it. So instead of vacuum, what you can do is you can use an iron rod. Which iron? Is it soft iron or a hard iron? Use a soft iron. Now I just want to check your knowledge, guys. For a soft iron, how is the hysteresis loop? Is it going to be narrow or broad?
Be narrow, sir.
It will be narrow because it has less retentivity and what is the other parameter? It's called something that starts with C. It has less retentivity and coercivity. Right? That is the reason why we need to use a soft iron, because we don't want magnetism to exist continuously. We don't. So as soon as the switch is removed, that is the work of a temporary magnet. Right? Temporary magnet should not have magnetism for a longer duration. That is the only reason where you see in all these electrical equipments like a transformer, AC generator, everywhere they will use only a soft iron core. Okay, that is an important point. Please make a note. Most of the places you will see the soft iron. Shariyada, am I clear? Second, so when I connect it, so okay, now I have another question. If I use a soft iron, what is the advantage? Forget about soft. If I use an iron instead of vacuum, what do you think is the parameter that is going to change the whole game? Guys, these are all slightly higher order thinking, but it's better you learn all these things.
So could you repeat the question?
Yeah, I'll do that. So I'm saying, see the diagram they show, let me explain it clearly. In the diagram that they show, right, does the coil C2 have any layer which is holding it, or is it only having air in between?
Only air.
Only air, right? So when it is having only air, instead of air medium, if I introduce a soft iron core like this, what do you think will be the advantage?
So the number of field lines passing.
It has nothing to do with number
The
of
magnetic property increases, sir.
magnetic
Property increases, like it gets
What
easily
property?
magnetized.
Yes, what you're saying is right. But what property of there is something, see, I'll give you a hint. There is something that is there in the magnetic properties. You remember we saw 8 points. Magnetizing field, magnetic induction.
It becomes a ferromagnet, sir.
It's a ferro. Iron itself is ferromagnet. Right? Iron technical name is ferro. It's a ferro. That is not the reason. Okay, I'll take your answer. Ferromagnetic is right. But what is the important property with respect to a ferromagnetic substance? I just
It
want
has
to see.
high intensity.
Not intensity. Intensity is okay. I'll tell it. It has high permeability. You guys remember there was one point called as relative permeability. Mu r is equal to mu divided by mu naught.
Yes, sir.
Okay. Now what will happen is mu will be equal to mu r into mu naught. Accepted? Where mu is the permeability of the soft iron. Mu r is the relative permeability of soft iron. You try to understand. Mu is the absolute permeability of whom? Of the soft iron. Exact value of. But what is mu r? Mu r is the relative permeability, and mu naught is already existing. Mu naught is the permeability of phase space. And you guys remember the table? I would have told you that mu r value is greater than 1000. Means
Yes, sir.
of air medium, if I introduce a ferromagnetic medium, what would happen is the permeability, the overall permeability of that material will increase by a factor greater than 1000. That is the advantage of using a soft iron core. See, I'm explaining all this story because you will see the soft iron repeated in multiple places. At the time, you should understand why they are using. Or else you'll simply memorize it. Don't do that. Okay, I hope my logic is clear.
Yes, sir.
Right? So I hope everybody made a note of it, right? Please write it down. Again, don't forget. So I'll give you a minute time. You can make a note of what I explained in your own words.
So since it's permeable, it allows more magnetic field lines to pass through it and increases magnetic.
That you can say that. If you mention the word, it has higher permeability. That is a keyword. Because whatever you told me, it increases the number of field lines, all those things. That is an interconnected topic. But yeah, if in your notes, if you want to write it like that, please do it. But in exam, when it comes, you can just say that the permeability of that electromagnet, the permeability of the medium will increase. That's it. That word is important. Permeability is the word important.
Okay, sir.
I hope I'm clear, right? Yeah. Okay. So that is by using a soft ion inside C2. That is the electromagnet. Or else what you can do is you can increase the magnetic field. So what they are concentrating is, since the area of the coil and the value of theta is fixed. That's the logic. That is the logic. I told you, right? Flux depends on three parameters. What are they? V, A, cos theta. Since the area of this coil is fixed, orientation is fixed, you can try to increase the magnetic field. So one of the ways of increasing magnetic field is increasing the permeability. Second is you can increase the value of current that is flowing through the electromagnet. But for you to increase the current flowing through the electromagnet, you obviously need a stronger battery. So we need to connect the coil to a powerful battery. Okay. Or the third one is move the arrangement rapidly towards the coil C1. I told you, right? When I move it fast, the glow is more. When I move it slow, the glow is less. So because in this scenario, motion is also an important thing. What you can do is you can control the motion by making it move fast. Okay. Next is, how would you demonstrate the presence of an induced current in the absence of a galvanometer? That's what I showed you in the simulation. You can either use a galvanometer or replace it with a small torch bulb, or you can use a small LED. Okay. Right? Example 6.2. It's a problem. See. So there is a square loop of side 10 centimeter and it has a resistance of 0.5 ohm. Is placed vertically in the east to west plane. There is a uniform magnetic field of 0.1 Tesla, which is set up across the plane in the northeast direction. The magnetic field is decreased to 0 in 0.7 seconds at a steady state. Determine the magnitudes of the induced EMF current during this time interval. Okay. Did you guys understand this question? Now tell me, what are all the parameters that we need to take? So they're asking, determine the magnitudes of the induced EMF and the current, induced current in this time interval. Now, since the time it is taking for the magnetic field to become 0 from 0.7 seconds, right? Do we need to calculate the average value or the instantaneous value?
Instantaneous, sir.
Zero, no, they told it decreased to 0 in this between 0 to 0.7 seconds. So between is always average value. If the preposition at is used, if they had the same question, the magnetic field is decreased to 0 at 0.7 seconds, then you should use instantaneous value. Am I clear?
Yes, sir.
Right. So now the question is, see, this is how I think. I'm just sharing the way I think. Okay. When I read a question based on electromagnetic induction, I'm damn sure when they say induced EMF, then there is only one parameter that is going to change with respect to time, that is flux. So for me to calculate flux, I will look in the question of what are all the parameters they have already given. So flux basically depends on three parameters. What are they? Magnetic field, area, and orientation. Now first, and If there are n number of turns, yes, it depends on the number of turns as well. So there is a square loop. So generally loop means one turn. Okay. If they use the word coil, then it is n turns. So I hope you guys are able to understand this word. Loop generally is a keyword for one turn. When they use the word coil, it means it is n turns. That is the meaning. Sharia. So here the number of turns is 1. Okay, accepted. Next. Area is how much? 10 into 10 power minus 2, the whole square. So is it not 10 power minus 2 meters square? Because it is 10 centimeter. Similarly, what is the resistance? 0.5 ohm or half ohm. A uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. This I told you already. What do you mean by northeast? Theta is equal to
45 degrees, sir.
45 degrees. You need to be careful with that. Now the magnitude of the magnetic field is decreased to 0 in 0.7 seconds. So delta T is how much? It is 0.7 seconds. So B initial is 0.1. B final is 0. Right? So we need to calculate the magnitude of the induced EMF. So when they say magnitude, just write it as delta phi B's magnitude divided by delta T. Delta T is always positive. So what is delta phi beta? Is it not final magnetic field, final area into cos theta final minus initial magnetic field, initial area into cos theta initial, the whole divided by delta T with a modulus. So B final is how much? 0. Okay, 0 into whole thing is going to be 0 only. I need not worry about other values. Minus B initial is 0.1 into area is 10 power minus 2 into cos theta I, cos of 45 degrees, the whole divided by delta T is 0.7. Put it within a modulus. So this will be 0.1 into 10 power minus 2 into cos 45 is 1 by root 2, the whole divided by 0.7. But remember, 1 by root 2 is 0.707, which can be approximated to 0.7. So this will go 7 times. Okay. So 0.7 into 10 power minus 2 divided by 7 is this value. That will be 0.1 into 10 power minus 2 Tesla, or 1 into 10 power minus 3 Tesla, and 10 power minus 3 Tesla is 1. Sorry, not Tesla, volt. Sorry. Volt. Am I clear, guys? No confusion, right? It's actually a simple problem.
Sir, but where do we use resistance in this, sir?
Where do we use resistance? It's not at over. Because I calculated only the induced EMF, but they asked induced current. No. Induced current is how much? E divided by R, induced EMF divided by resistance. So 1 into 10 power minus 3 divided by, what is the resistance? It is half. So it will be 2 into 10 power minus 3 ampere or 2 milliampere. Got it?
Sir, understood.
Shall I proceed, guys? Shall I proceed to the next one?
Yes, sir.
Okay. Now see. There is a circular coil of radius 10 centimeter. So radius is 10 into 10 power minus 2 meter. And it has 500 turns. Resistance is 2 ohm. Is placed with a plane perpendicular to the horizontal component of the Earth's magnetic field. Is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about its vertical diameter through an angle of 180 degrees. So theta through which it has got rotated is 180 degrees. In the time delta t as 0.25 seconds. In means average. At means instantaneous. Estimate the magnitudes. Magnitudes means positive value of the EMF induced current where the horizontal value of the Earth's magnetic field is given as 3 into 10 power minus 5 Tesla. Okay. So here again, if I need to calculate the EMF, what do I need? I need the change in magnetic flux with respect to time. So B final, A final, cos theta final minus B initial, A initial and cos theta initial, the whole divided by delta t. So what is the value of B final, guys? Whether you talk about B final or B initial, the value is fixed. It is 3 into 10 power minus 5 Tesla. So 3 into 10 power minus 5 into, what is the final area? The final area is also pi r square only. So if I take that common, if I take those values common, B into A divided by delta t, then what is going to be different? Cos theta phi minus cos theta initial.
Sir, can you explain how you took it common, sir? On what basis you took B and A
Because
common, sir?
they're same, no? It's the same coil. Same coil. So it's the same magnetic field. The horizontal component of the Earth's magnetic field is fixed at the given location. So only thing, so here the flux is changing only because of the change in the orientation. You're able to understand? So flux is equal to BA cos theta. So B is constant, A is constant, theta is changing in this case. Because initially theta was 0 degrees, finally theta is 180 degrees because it is rotated through an angle of 180 degrees. So that is the reason I took them common. Am I clear?
Sir, but how you took A common, sir? It's circular, but
The
Earth
same
is
coil.
not circular. No, sir.
Right. Area of the coil. Circular coil. Circular coil of radius 10 centimeter. So when its radius is fixed, obviously area fixed. Area
Okay,
is pi r
sir.
square. Got it? You don't take the area of the Earth. You take the area of the coil. And in that place, the magnetic field that is present is the horizontal component of Earth's magnetic field. So, yeah. So
Okay,
that is the
sir.
meaning. Yeah. What was I telling? Yes. B is there, A is there. So B is 3 into 10 power minus 5. Area is pi into r square. That is 10 into 10 power minus 2 the whole square. The whole divided by 0.25. 0.25 you can actually take it as 1 by 4 into cos theta final is cos 180 degrees minus cos theta initial is cos 0 degrees. Okay. So cos 180 is minus 1, cos 0 is 1. So minus 1 is minus 2 actually. Then calculate the value. Those many Tesla will be the answer. Actually, in this case, you will get a negative value, but take a modulus. Why are we taking modulus? Because they asked only the magnitude. Sharia. Please note down. And calculation part alone, I'm leaving it. Sorry guys, one more thing to be added. I missed the number of turns. So I can write it as n times 5b. So here also it will be n and we need to multiply with 500. Guys, is everyone clear or you want me to clarify any of the steps? Everything is clear?
Yeah, actually, I have a doubt.
Tell me.
formula will have a negative sign already, right? So it should be minus NVA by delta.
Okay, you can take it like that also. But since they ask magnitude, just put a modulus. Okay. Because minus sign is actually used to find the direction of induced EMF, which is the next topic. So I don't want to confuse you with both things. That is why I'm doing it slowly.
Okay.
Okay. Right. After you find the EMF, what are you supposed to do? Divide that value with the given resistance. That is 2 ohm. Then the answer will be those many amperes. Okay. Can I rub this, guys?
Yes, sir.
Now I'll give you an introduction of what does Lenz's law mean. Okay. So Lenz's law is basically a concept which depends on the principle of conservation of energy. So Lenz's law and conservation of energy. Okay. Let's how to do this. Now see. Let's take this example itself. Okay. Now I want you guys to observe one thing here. So by now, I'm sure that you guys understood that if there is a change in flux taking place with respect to time, EMF is induced. Okay. Accept. But the second question that we need to answer with respect to EMF is about the polarities. What do I mean by polarities? I need to be sure of which is positive terminal and which is negative terminal. Correct, Ada? It is then I can decide the direction of current. Okay. So what happens is generally if the direction of current is changed, the deflection of the galvanometer will also get reversed. The best example is the same simulation. Observe, when I move the magnet towards the coil, I hope everybody is observing. When I move the magnet closer to the coil, the deflection of the galvanometer is in the leftward direction. But if I move the same magnet away, did you observe that the direction of current has changed? Guys, are you able to understand? So if a galvanometer is given in your hand, how will you test whether it is working or not? So the best way to check a galvanometer if it is working or not is take the galvanometer and connect the galvanometer to the positive and negative terminals of a battery. Then observe the direction of deflection. I repeat, take a galvanometer, connect it to the positive and the negative terminals of a battery and observe the direction of deflection. Then reverse the polarity. Take the same two wires and swap the polarities. Means initially the first wire was connected to positive, second to negative. Now do the reverse. Take first and connect it to negative and the second and connect it to positive. Then what should be the deflection? Should it be in the same direction or opposite direction?
Opposite.
It should be in the opposite direction. So yeah. So the same thing is happening here. Now I'm going to look at the same concept with a different perspective. So I will call it as when the north pole is moving towards a coil, I observe the deflection to be on the left-hand side. When the same magnet is moved away from the coil, the deflection changed. When the same north pole is moved away from the coil, then the deflection changed in which side? Exactly in the opposite side. Now, what does this Lenz's law have to tell us? That's what the question is. So if I take a coil like this, and if I have a north pole and a south pole, if I move the north pole here, now I have one question. Think and tell me. When I'm moving the north pole towards the coil, am I increasing the flux or decreasing the flux?
Increasing the flux.
I'm increasing the flux. Due to what reason? Due to the reason that we know that magnetic field lines are closer. They are more dense near the poles of the magnet. So when the pole of the magnet is moved towards the coil, then the magnetic flux is increased. So when the magnetic flux is increased, what will happen with respect to Lenz's law is the coil which is facing the magnet will behave like a north pole. Okay. Will behave like a north pole. Means if any particular pole is taken closer to the magnet, then the magnet will start generating the same polarity. Okay, have this point in your mind, how and everything, that I'll explain it tomorrow. But I'll just give you an outline perspective of what is Lenz's law. So when I move north pole closer to the magnet, what pole will get generated? The side, the coil which is facing the magnet will generate the same pole. In a similar way, had the north pole been moved away from the magnet, then what would have happened? Then south pole would have got generated. Am I clear? So this is what happens. And this particular phenomenon is due to the concept called as Lenz's law. Okay, so what that Lenz's law is, we'll see it in tomorrow's class. So to show you the diagram from textbook, observe this. When the north pole of the magnet is moved closer to the coil, then it generates a north pole. And if the same magnet is moved away from the coil, then it generates exactly the opposite pole. Now the question is, what will happen if the south pole is moved? So if the south pole is moved towards the magnet, then what would have happened here is south pole would have got generated. But if the south pole is moved away from the magnet, then north pole would get generated. Clear, guys?
Yes, sir.
Yes, sir.
So this is what is the significance of Lenz's law. Okay. Are you able to understand? So
Yes, sir.
this is the reason why the Faraday's law has a minus sign, because everything is happening in the opposite direction. Okay, I'll show you. Okay, that I will show it in tomorrow's class. If it is clear till this point, we can wind up. If there is any doubt, you can ask me.
Sir,
Tell me.
sir, actually you said that when there is change in magnetic flux, electricity is generated. But then in the
Correct.
simulation, when the number of magnetic field lines did not change, when you just moved it a little nearer, that time also the change in voltage was shown, no, sir?
Yeah,
So,
change happened because, can you tell me why?
because the intensity of magnetic field line
That's right.
increased.
Perfect. Perfect. Yeah, now tell me what is your doubt.
I wanted to make sure of that.
That's right. That's right. Because flux depends on three parameters, right? B, A, cos theta. A and theta were same when we moved. The number of field lines was still 4 only. But what happened? The strength was more, because if you observe the distance, no, distance was less. Correct? That is the reason why the intensity was. You're right. That is the reason why flux is changed.
Okay.
Yeah.
Sir, I have a doubt
Yeah.
regarding upcoming tests. Sir.
Tell me. Tell me.
Will it be in the new format like
No,
CBSE or
not
will
you.
it be not?
Because I don't have any blueprint. I don't know how the paper is going to be. The blueprint, we got the syllabus itself recently only. No? So as of now, I'll conduct subjective, because I want to know how much you people are studying. That is important for me,
sir.
because then I can help you. No? Then after the new pattern comes, don't worry. That kind of question papers will also come off. We will create it. Don't worry. But when the blueprint is released or sample papers are released, then we will conduct it according to the new pattern.
Okay, sir.
Okay. Yeah. Okay, then we can wind up, guys.
Thank you, sir.
Thank you.
Thank you, sir.
Yes, sir.
Sir. Sir, can you hear me? Sir, I can't hear you. Sir, am I audible?